Okay, so in this next chapter, we're going to step away from stoichiometry and talk more about how things react at the molecular level, how things change from being a reactant into a product at a very small scale. So what we're going to talk about is something called the collision theory. The collision theory says that molecules have to collide in order to react. And the reason for that is that they have to break old bonds and new ones have to form. So they have to bump into each other to make that happen. The more often they collide, the more likely they are going to react. Not every time things bump into each other does a reaction occur. Only when certain things are met. But the more often they collide, the better the chances are that they will react. So one of the ways to increase the rate of reaction, make it go faster, is to increase the concentration. The more reactants you have floating around, the more likely they're going to collide and they're going to react. It's pretty simple, pretty obvious. If it is a solid reactant, those tend to have a hard time reacting. But if you increase their surface area, in other words, you don't have one big chunk of solid, but you have lots of little chunks of solids, or you stir it up, that increases their chances of colliding with something else and increases the rate of reaction. If it's a solution or a liquid, one of the best ways to do it, make it go faster, is to add more. And then for gases, this is a little bit different. What you want to think about is gases are very spread apart. Those molecules very rarely come in contact with each other. So if you increase the pressure or you decrease the volume, you're going to bring those molecules closer together. So the second thing they have to do, they have to collide, but they have to collide with sufficient energy to break the bonds. And that is affected by two things. Temperature affects the rate very much for a couple of reasons. Number one, there are more collisions and a greater energy associated with each collision. You have to give them enough energy to collide with each other more often, and every time they hit, they have to hit harder. Okay, and then the second thing is that the molecules have to collide in the correct orientation. They have to line up properly so that new bonds can form. And it's often called the steric factor, and I'll show you on the next slide what that looks like. So here we have our molecule BRNO colliding right here on the BRs. And when that happens, it can break the bond between the BR and the N's, and we get a BR and 2 NO. So the equation is 2BRNO goes to BR2 plus 2 NOs. And if they collide like that, perfectly logical that they would react. If they collide end to end, same thing. They could sever the bond here and form a new bond where you have, again, a BR2 and 2 NOs. But if they collide here, there's no way to sever the bond between the BRs and have them form the BR2. So this is an instance where there would not be a reaction. They wouldn't collide properly to make that reaction happen. Some important definitions for you. Activation energy is the minimum amount of energy needed to make a reaction happen. So if it doesn't have that activation energy, the reaction doesn't happen. That's why temperature helps a great deal, because temperature adds more energy. The bigger the activation energy is, the slower the reaction generally is. It is determined by temperature and steric factor. The activated complex, or the transition state, is what the molecule looks like at the moment of collision, the moment it hits. It's a temporary state. And what we're going to talk about is we're going to talk about these things called energy profiles. And they're going to graph potential energy versus time, essentially. They show the reaction in terms of the energy of the reactants, the products, and the activated complex. So this is what one looks like. These are my reactants. And these are my products. And this is literally a graph. This could be 0, and this could be considered to be time. And so if I was to measure the potential energy of my reactants, they would be from 0 to wherever the reactants live, maybe 150. whatever it is, okay? If I was to measure the potential energy of my products, they are at a lower potential energy. Maybe they're only at, say, 50, okay? And so in order for my reactants to turn into my products, these two molecules have to collide. They have to collide in the correct orientation, and they have to collide with enough energy to make it over the hill. And this hill represents the amount of energy it takes for them to turn into the products, because up here is the activated complex. What happens when they actually collide at that moment of collision, and it has a lot of potential energy. Oops, wait a minute, go back. And so for these reactants to get to the top of that hill, they have to gain energy, and that energy is the activation energy. That's how much they have to gain. Once they gain it and they're at the top of the hill, they turn into the products very easily. Okay? The difference between where the products and the reactants are, so products minus reactants, that is referred to as delta H, and you might remember that from when we were doing heat. So that's kind of a summary of this. This is overall an exothermic reaction because the products have less potential energy than the reactants do. Okay, so this is what the transition state looks like. That's the activation energy. It's how much it needs to get over the hill. That's delta H. What a catalyst does, and you might remember this from bio, is it speeds up a reaction without being used up in the reaction. You may have learned about enzymes in biology. In chemistry, we have two different kinds of catalysts. We have homogeneous catalysts. That means they're in the same phase as the reactants. I don't see that very often. Usually I see ones that are heterogeneous. They're in a different phase. But it's just a matter of being what they are. So how catalysts work is they allow reactions to proceed by a different mechanism. They help them collide better. Remember, there were three things in order for a reaction to take place. They have to collide with energy, and they have to collide in the correct orientation. And what catalysts do is they help them line up properly. And it predominantly affects the steric factor, makes it easier for them to collide. The new pathway has a lower activation energy, and so therefore more molecules will have that activation energy and will make it over the hill, and their rate will increase. It does not change delta H. All it does is change the hill. So it looks like here's what my catalyst does. Kind of like provides a tunnel through the hill. Doesn't change where I start, doesn't change where I end up. All it does is make the activation energy less. Okay, instead of having to go all the way up to the top up here, they can only go up to here, and that's why more of them react when that happens. So this is a sample problem. Identify the following: the potential energy, the reactants, the products, the activated complex, and activation energies, and delta H. So first of all, my reactants are always here, my products are always here, and the activated complex is always there. So for my reactants, they are starting at a very low potential energy. My products are at a very much higher potential energy. And then the activated complex has the most potential energy of all, because it doesn't normally exist. In order for the reactants to turn into products, they have to climb this very large hill. That is referred to as activation energy, from where the reactants are to the top of the hill. If the reaction goes in reverse, and we're going to start talking about reversible reactions, my products can turn backwards into my reactants by climbing a much smaller hill. And then if I put a catalyst in here, I'm going to do that in a different color. What a catalyst does is it makes the hill smaller. So if I was to put in the activation energy for the catalyst, it is much less than the activation energy for the normal reaction. Delta H is the difference between where the products and the reactants are. And overall, this one is endothermic. And the second part of our lesson about reaction mechanisms, or about kinetics, deals with something called reaction mechanisms. They are the series of steps that actually occur in a chemical reaction, if you could actually see what's happening. It's step by step how the reactants collide and turn into products. And the reason they exist is because in the collision theory, molecules have to collide at the same time and line up properly. Well, if you think about it, it's not possible to have more than 3 molecules collide at any one time. And so the rule for reaction mechanism is you're not allowed to have more than 3 reactants in any one step. Kinetics will tell us something about the reaction mechanism. If you take AP chemistry, you'll learn about that. The mechanism has to describe the stoichiometry, so it has to add up correctly to the overall reaction, and each of the steps has to be in correct order to justify the next step, kind of set up the next step for working. For example, this reaction occurs, okay, 4 HBr and an oxygen. That's 5 molecules that have to collide at one time to react and form water and bromine, but it happens. We know it happens, and that's how many balanced equation, that's how many molecules collide. However, it can't happen like that because that's 5 molecules colliding at once. So here's a proposed mechanism that someone came up with. I don't expect you guys to come up with a mechanism, but I want you to think about it as a series of steps that describe how the reaction takes place, where only 1 or 2 or maybe 3 molecules in each step collide. So for example, in this one, HBr and oxygen collide to form, I'm going to call it Huber. That's a very slow reaction. It takes a long time for that thing to happen. But as soon as Huber is made, it's kind of like a domino effect. Huber reacts with an HBr and forms 2 Hobers. And that goes very, very quickly. And then each one of those Hobers goes out and finds another HBr and forms a water and a bromine. Okay? And so this one, to show that it adds up to an acceptable mechanism, all you have to do is confirm that there are no more than 3 reactants in any one step, and there are not, and it adds up to the stoichiometry. So the way you do the stoichiometry part is treat this like an equal sign. And if there are compounds or elements on opposite sides of the arrow that are identical, so Huber and Huber, they cancel out. And 2 Hobers, I have 1 and 2 Hobers. They're on the same side, so they add together. These 2 Hobers cancel out with that. And so what I'm left with is 1, 2, 3, 4 HBr plus an oxygen. They're all on the same side of the arrow, so they add. Turns into 2 waters and 2 bromines, and they're on the same side of the arrow, so they add together. So that's really what you have to do. For a mechanism, you have to make sure that there isn't more than 3, and you want to make sure what it adds up to by canceling out things that are the same on opposite sides of the arrow. So for that reaction, that mechanism, which 2 substances determine the rate? So this is the hard part. This is the kinetics part of it. If you look at it, it takes a very long time. It says it's very slow for those 2 to react. And if you think back to our activation energy, what that means is my reactants start pretty low and they have a really big hill to climb. It takes a long time to get to the top of that hill. It has a very high activation energy. And because they are very slow, they act like a bottleneck. They slow everything else down. As soon as Huber is made, the domino effect is off and running. But it takes a very long time to make that Huber. So the 2 substances that determine the rate are HBr and oxygen in the slow step. Very often that slow step is referred to as the rate determining step. Not great handwriting there, sorry. And what are the formulas of intermediates? These are the ones that you cross out. Ones that are made and then immediately used. So I crossed out Huber and I crossed out the Hobers. Those are the intermediates. Okay? Now, how it ties into the collision theory is every step in a mechanism has an activation energy. I kind of talked about that a little bit before. The activation energy determines the speed of the reaction, because again, it's the hill. They have to climb that hill. They have to have enough energy to get over the hill. Once they do, the reaction's off and running. But the slowest step is referred to as the rate determining step. It must have the highest activation energy. It's the biggest hill because it's the slowest one. It takes the longest time for them to get over. So here's an example. Doesn't match exactly what we had with Huber and Hover, but it's a three-step mechanism. In each step, that's the activation energy for the first step. It's very fast. It's not a very big hill to climb. Okay, it has a low activation energy. The second step is the slowest one of the bunch because if you look at it, those, whatever the reactants are here in this second step, have a very big hill to climb. They need a lot of energy to get up there. In the third step, they only have to climb a very small hill. It doesn't take very long. The second step is rate determining. It would be the one that says slow. Activated complexes, this is what happens when they collide. And then those are where the intermediates are. So my Huber and my Hovers. Okay? Even though it doesn't match because that was a four-step mechanism. So on this one, identify the potential energy of the reactants. We are talking at the very beginning for the reactants and the products at the very end. So this is the potential energy for the reactants. This is the potential energy of the products. Energy of reaction, that's delta H. That is always the difference between wherever the products are and the reactants are. So that's my reactants, that's my products. The difference between where I start and where I end up is delta H. Activation energy 1 is the first hill, quite large. Activation energy 2 is just the second hill. Which step is rate determining? That would be the first step because it is, if I split it this way, this is step 1 and this is step 2. This has the biggest hill to climb. Which step would be most affected by a catalyst? Now that's a great question because remember what a catalyst does? Is it makes the hill smaller. Which one has a greater effect on the activation energy? Well, here versus here. The difference is that versus this. Step 1 definitely has the greater effect on it with a catalyst. And then overall, is it exothermic or endothermic? Reactants start low, products start high. It's endothermic.